Hi, this is SM and welcome back to our channel Concept of Mechanical Engineering. In the previous class, we have completed the numerical part of work transfer. Now we are going to move on our next topic, which is heat. In heat, we will study heat transfer. Heat transfer. What is heat transfer? The energy transfer by virtue of temperature difference is known as heat transfer. So when there is a difference in temperature, then there is a transfer of energy, and this transfer of energy is known as a heat transfer. So the transfer of energy by virtue of temperature difference is known as heat transfer. It is denoted by Q. Its unit is kilojoule. So the direction of spontaneous heat transfer is from higher temperature to lower temperature. So when there is a difference in temperature, and that is from higher temperature, heat transfer occurs. And there are different modes of heat transfer like conduction, convection, radiation. We will study these modes of heat transfer in the heat transfer subject. So now let's see one thing. We have studied PV diagram in work transfer. So this is our PV diagram. This is P axis and this is V axis, and this was the process. Let us consider this process from 1 to 2. This is quasi-static process. Then the area under the curve on PV diagram is the work transfer. This we have studied in the work transfer chapter. This area is work transfer. In the same way, for heat we have TS diagram, where T is the temperature and S is the entropy. We will study the detail about this property, entropy, in upcoming chapters. So let us consider a curve. This is quasi-static curve, quasi-static process from state 1 to state 2, and the area under the curve, this area on TS diagram, this area is the heat transfer. This area is heat transfer. So the area under the curve on PV diagram is work transfer, and the area under the curve on TS diagram is heat transfer. So in the work we have the general equation as work transfer from 1 to 2 is the integration of dW from 1 to 2 is equal to integration of pdV from 1 to 2. Similarly, in for heat transfer, we have heat transfer from 1 to 2 is equal to integration of dQ from 1 to 2 is equal to integration of TdS from 1 to 2, where T is the temperature and ds is the change in entropy. So here in work transfer, P is the pressure and dV is the change in volume. In work heat transfer, T is the temperature and ds is the change in entropy. Here this T is intensive property, and S is extensive property. So heat transfer is equal to the integral of the product of intensive property and the special change in extensive property. Now Q is directly proportional to delta T, change in temperature, and Q is also directly proportional to M. So Q is directly proportional to M delta T, and if we remove this proportionality sign, then we get a constant which is C. So Q is equal to MC delta T, and this constant is known as specific heat, and this is given as C is equal to Q by M delta T. Its unit is The unit of Q is kilojoule, the unit of mass is kg, and the unit of temperature is Kelvin. So the unit of specific heat is kilojoule per kg Kelvin. Now if m is equal to 1 kg and the change in temperature either increase or decrease is equal to unity, then the heat transfer required to fulfill this condition is known as a specific heat. So when the mass is 1 and the change in temperature is unity, then the heat transfer required to fulfill this condition is known as a specific heat. So a specific heat. The amount of heat transfer required to raise the temperature of a unit mass of a substance by unit degree temperature difference is known as specific heat. So specific heat is defined as the amount of heat transfer required to raise the temperature of a unit mass by a unit degree temperature difference is known as specific heat. Now the sign convention of heat transfer. The sign convention of heat transfer is arbitrarily chosen. So the most common followed is, let us consider this system. So heat supplied to the system is positive. Heat supplied to the system is positive, and heat rejected by the system is negative. Heat rejected by the system is negative. So when there is addition of heat or heat supplied to the system, then it is considered as positive, and when there is a rejection of heat, that is heat is removed from the system, then it is considered as negative. This is the sign convention used in heat transfer. Now note one thing: solids and liquids are incompressible, and hence solids and liquids have only one specific heat, but for gases there are two specific heats. Cp and Cv. So for solids and liquids, the specific heat does not depend on the process, but for gases it depends on the process. If the process followed is a constant volume process, so then it is Cv, and if the process followed is constant pressure process, then it is Cp. Now let us compare the value of Cp and Cv. So Cp at constant pressure and Cv at constant volume. This is Cv, and constant pressure Cp. Let us consider a piston cylinder arrangement. This is our piston cylinder arrangement. This is the piston, and a stopper is fixed here so that the piston does not move up. Let us consider the cylinder is filled with a gas A having mass 1 kg, and our aim is to raise the temperature of this gas by 1 degree. So delta T 1 degree, our aim. So to fulfill this aim, we supply heat. Let's Q1 is the heat. So this Q1 is the heat supplied to increase the temperature of the gas A by 1 degree, and this heat is equal to the specific heat at constant volume. Now let us draw another piston cylinder arrangement of same size as of this one. This is the same size piston cylinder arrangement, same size, and the same gas is filled in this cylinder having the same mass 1 kg. Now there is no any stopper, it is free to move up. Now a heat is supplied, let's say Q2, to raise the temperature, because here also that we have the same aim to raise the temperature by 1 degree. So to fulfill this condition, we supply heat Q2 to raise the temperature by 1 degree, and this heat is equal to the Cp, that is specific heat at constant pressure. So let us see here, this is increasing the internal energy of the gas A, and this heat is equal to Cv. But here that heat is supplied which is raising the temperature of this gas, as well as it is doing an external work, PdV work, because it is free to move. Now the piston will move here after some time. So the amount of heat which is supplied to this piston cylinder arrangement is used to increase the internal energy of this gas, as well as it is doing an external work. So from here Q2 is greater than Q1 because it is increasing the temperature as well as it is doing an external work. But here it is only increasing the temperature because it is only increasing the internal energy of the gas A. So Cp is greater than Cv, and the ratio Cp by Cv is equal to gamma, which is greater than 1. Now note one thing. The specific heat at constant pressure, that is Cp, is greater than specific heat at constant volume, that is Cv, because Cp includes both internal energy and external work. But Cv includes only internal energy. Now effect of variation of temperature on Cp and Cv. For ideal gas, the value of Cp and Cv remains constant. That is, it is independent from the temperature. But for real gases, both Cp and Cv increases with the increase in temperature. For diatomic and triatomic gases, but their difference is constant. is constant, that is Cp minus Cv is equal to constant, which is R, known as characteristic gas constant. Characteristic gas constant. But for monoatomic gases, Cp and Cv both remains constant. So for ideal gas, Cp and Cv remains constant, but for real gases, for diatomic and triatomic gases, Cp and Cp both increases with the increase in temperature, but the difference is constant, which is known as characteristic gas constant. But for monatomic gases, the specific heat capacities remains constant. Now for real gas, Cp, Cv, gamma is a function of temperature, pressure, volume. From ideal gas equation, we have PV equals to mRT and PV equals to nR bar T, where R bar is the universal gas constant. Universal gas constant. Same for all gases. Its value is 8.314 kilojoule per kilomole Kelvin, and this R is characteristic gas constant, and its value is different for all gases. Now if we divide both these equations, we get R is equal to N by M R dash. This is the relation between characteristic gas constant and universal gas constant, where N is the number of moles, M is the mass, and we know that N is equal to mass by molecular weight. From here we get molecular weight is equal to M by N. So substituting this value here, we get R is equal to R dash by M. So R for O2 we have 8.314 by molecular weight of oxygen, which is 32. R for H2O, it is 8.314 by 18, and R for NH3 we have 8.314 by 17. Its unit is kilojoule per kg Kelvin. This is molecular weight. Now for air, we have Cp equals to 1.005 kilojoule per kg Kelvin, Cv equals to 0.718 kilojoule per kg Kelvin, R is equal to 0.287 kilojoule per kg Kelvin, and gamma equals to 1.4. kilojoule per kg Kelvin. This is the value of Cp, Cv, R and gamma for air, which is treated as ideal gas. Now let us see one question. A steel ball of mass 1 kg of a specific heat 0.4 kilojoule per kg Kelvin is at a temperature of 60 degrees centigrade. It is dropped into 1 kg of water at 20 degrees centigrade. The final steady state temperature of water is. So we have to find the final temperature of water. So what's given in the question? For steel ball, we have mass of steel ball 1 kg. This one, a specific heat of steel ball 0.4 kilojoule per kg Kelvin, 0.4 kilojoule per kg Kelvin. Initial temperature of steel ball is 60 degrees centigrade, and for water, mass of water, this is 1 kg. Specific heat of water, we know it is 4.18 kilojoule per kg Kelvin, and the initial temperature of water, we have 20 degrees centigrade. We have to find the final temperature of water. The final temperature of water and the steel ball will be the same because the steel ball is immersed, that is, it is kept inside the water. So let us consider final temperature as TF. Now applying energy balance equation, we have heat lost by the steel ball is equal to the heat gained by the water. Whatever the heat lost by the steel ball, it is equal to the heat gained by the water. So heat lost by the steel ball is equal to heat gained by water. Now heat loss by steel ball is mc delta T, that is ms cs, and delta T, that is this 60 minus TF, because the temperature, final temperature of steel ball will be less than compared to the initial temperature, because it is the heat is lost from the steel ball. And for water, mw cw of water into T final minus 20, because the temperature of water will increase, so T final minus 20. Mass of steel ball 1 into CS 0.4 into 60 minus TF is equal to mass of water 1, Cw of water 4.18 into TF minus 20. From here we have 24 minus 0.4 TF is equal to 4.18 TF minus 83.6. From here we get 4.58 TF is equal to 107.6. Solving 107.6 by 4.58, we get 23.5 degrees centigrade. So the final temperature of water is, temperature of water is 23.5 degrees centigrade. That is, option A is correct. Answer option A. Now another question. A 2 kilowatt 40 liters water heater is switched on for 20 minutes. The heat capacity Cp for water is 4.2 kilojoule per kg Kelvin. Assuming all the electrical energy has gone into heating the water, increase of the water temperature in degree centigrade is. option A 2.7, option B 4, option C 14.3, and option D 25.25 degrees centigrade. So we have it is given in the question that a 2 kilowatt 40 liters water heater is switched on for 20 minutes and all the electrical energy is used to heat up the water. So find the final temperature of the water. So we know that power is equal to heat supplied by time in second. So we know that heat supplied is here Q. So Q is equal to power into time. It is given power 2 kilowatt, 2 into and time for 20 minute, 20 into in second. If we convert 20 into second, we multiply by 60. So this will come in kilojoule, and this Q is used to heat up the water. So energy gained by the water, heat gained by the water is equal to Q is equal to mCp delta T. Therefore Q is equal to mCp delta T. The value of Q is 2 into 20 into 60 is equal to mass of water. Volume of water is given. So volume of water is 40 liter. If we convert this in meter cube, we multiply it by 10 to the power minus 3. We get the meter cube. We know density is equal to mass by volume. So mass is equal to density into volume. Density of water is 1000. So 1000 into 1040 into 10 to the power minus 3. Here we get the mass of water as 40 kg. Substituting the value here, 40 into Cp of water, it is given 4.2. We have kept the value for Q in kilojoule, so we are keeping this the value of Cp in kilojoule, 4.2 into delta T. From there, delta T is equal to 2 into 20 into 60 divided by 40 into 4.2. On solving, we get delta T is equal to 14.3 degrees centigrade. That is, answer is option C is correct. This is the answer. Now, a football was inflated to a gauge pressure of 1 bar when the ambient temperature was 15 degrees centigrade. When the game started next day, the air temperature at the stadium was 5 degrees centigrade. Assume that the volume of the football remains constant at 2500 centimeter cube. The amount of heat lost by the air in the football and the gauge pressure of air in the football at the stadium respectively equal. So we have given the initial condition, gauge pressure 1 bar and the ambient temperature was 15 degrees centigrade. When the game started next day, the air temperature at the stadium was 5 degrees centigrade. That is final condition. We have given 5 degrees centigrade. Assume that the volume of the football remains constant at 2500 centimeter cube. So volume is constant here. So we have a constant volume. Initial temperature this one, final temperature this one. We have to find the amount of heat lost by the air and the gauge pressure of air. So let's solve this. Initially the gauge pressure is 1 bar equal to 100 kilopascal. Now absolute pressure is equal to gauge pressure plus atmospheric pressure. The value of gauge pressure is 100 plus the value of atmospheric pressure is 101.325 kilopascal. So the value of absolute pressure is 201.325 kilopascal. Now initial temperature T1 is equal to 15 degrees centigrade is equal to 15 plus 273, that is 288 Kelvin. So if we convert it in Kelvin, we add 273. Now final temperature T2 is 5 degrees centigrade is equal to 5 plus 273 is equal to 278 Kelvin. Now applying ideal gas equation in the first stage. So we have P1 V1 equals to V is constant, so PV P1 V is equal to M R T T1. From here P1 we have 201.325 into volume we have 2500 centimeter cube. If we convert this one in meter cube, we will multiply this one by 10 to power minus 6 is equal to M is equal to R. The value of R is 0.287 into T1. It is given 288. By solving we get the value of M as M equals to 6.089 into 10 to power minus 3 kg. Now heat lost. Is equal to mCV delta T, because constant volume, so mCV delta T. Mass we have calculated 6.089 into 10 to power minus 3. CV we have 0.718 into delta T, 288 minus 278. So we get the value of heat lost Q is equal to 0.0437 kilojoule, that is 43.7 joule. So we got the value of Q as 43.7 kilojoule. Now the second part, which is the gas pressure of air, we have to find that. So at V equals to constant, we have P1 by P2 is equal to T1 by T2. This implies P2 is equal to P1 into T2 by T1 is equal to P1 we have 201.325 into T2 we have 278 and T1 we have 288. On solving we get P2 as 194.33 kilopascal. Now we have P absolute is equal to P gauge plus P ATM. So P gauge at condition 2 is equal to P absolute minus P ATM. P absolute we have 194.33 minus P ATM we have 101.325. On solving we get P gauge 2 as 93 kilopascal is equal to 0.093 bar. So from here we have Q as 43.7, which matches with the option D, and absolute pressure, gas pressure is equal to 0.93 bar. This matches, so this is our answer. So option D is the answer. Now second part of the question, gauge pressure of air to which the ball must have been originally inflated so that it would be equal to 1 bar gauge at the stadium is, that we have to find the initial gauge pressure such that the final gauge pressure is 1 bar. So final gas pressure P gauge 2, it is given as 1 bar is equal to 100 kilopascal. Now final pressure P2 is equal to P gauge 2 plus P ATM. P gauge 2 we have 100 plus P ATM 101.325 kilopascal. So from here we get the value of P2 as 201.325 kilopascal. Now at V equals to constant, we have P1 by P2 is equal to T1 by T2. This implies the value of P1 is equal to T1 by T2 into P2. P1 is equal to T1 by T2 into P2. T1 we have 288, T2 we have 278 into P2 we have 201.325 kilopascal. So on solving we get the value of P1 as 208.56 kilopascal. Now P1 is equal to P gauge 1 plus P ATM. P1 we have 208.56 is equal to P gauge 1 plus P ATM we have 101.325. P gauge 1 is equal to 208.56 minus 101.325. On solving we get the gas pressure as 107.235 kilopascal. Therefore Pg1 is 1.07 bar. So option C is correct. Option C is correct. Today we have studied heat, specific heat at constant volume, specific heat at constant pressure, and some relation of ideal gas equation. In the next class we will start first law of thermodynamics. If you like this video and find helpful, please like, subscribe and share with your friends. See you in the next class.